Okay, hi everyone. Thanks very much for coming to this talk. So this is, as was mentioned, this is distributed statistical inference with PyHF, and I'm presenting today on behalf of the PyHF core development team. So that's Jordan Stark, myself, and Lucas Heinrich. And then we also want to call out Ben Galuski for his help in getting a lot of the funcX stuff up and running. Okay, so today is going to be a little bit different than I originally planned due to some hardware issues. The live demo that I had planned to show today is not going to work due to some issues beyond our control on some servers. So as a result, this all kind of got rewritten at the last moment. And also as another small note, due to what I've now learned is considered a security concern on opening ports, this is not going to be fully runnable on the MyBinder public instance. But as to try and combat that and still make sure that people can follow on if you want, I'm going to try and do all of this live so that if just to try and show people that if you're interested in following along, that it'll be okay. Okay, so to begin with, we're just going to go to the linked GitHub repository that's on the page, and we're going to go ahead and we're going to get the URL, and then I'm just going to go ahead and clone this down. So you should hopefully see my terminal at the moment. Okay, and then I already have a virtual environment set up, so I'm going to activate that, but if you don't have one, you should hopefully make one as well. And then I didn't really install anything in this virtual environment already, with the exception of just Jupyter and Jupyter Lab, just because those take a little bit of time. But if we go ahead and go into our notebook, then we're now going to go ahead and install all of our actual dependencies. So we're just, and those live under the binder directory. So we're going to do pip install -r binder requirements. And you can see that while we have a few, they all install pretty quickly. They're not actually that heavy. So this should hopefully install for you in just a minute or so. Okay, we're still waiting here for the final bit of the installation. Okay, so now we're up and running, and now we're just going to run Jupyter Lab, and we should get a instance popping up here now. And we're now going to just kind of walk through the kind of toy demo, not really a live demo, that I was originally hoping for. Okay, so this is going to first start off with just a super cursory introduction to PyHF. As Oksana mentioned, we aren't going to be doing a full tutorial for PyHF at PyHEP 2021. However, we have a tutorial that is a Jupyter book that is live all the time, linked here off of the PyHF GitHub organization. And then we also gave a CHEP 2021 talk that's on pretty similar material to this, so we'd invite you to check both of those out. But just in a short sentence for those of you who aren't familiar with what PyHF is, it's a pure Python implementation of the HistFactory family of statistical models. And so for those of you who aren't familiar with HistFactory, I'm not going to go into that here, but you can basically just think of it as a family of bin statistical models that has been used quite successfully at the LHC. It's one of the models that was used by Atlas for the Higgs discovery. And PyHF, in addition to being pure Python, also supports optional computational backends such as like JAX or PyTorch or TensorFlow that provide automatic differentiation as well as hardware acceleration on GPUs to try and give you really snappy and speedy fits. And PyHF is also part of scikit-HEP, and it's designed to have a very clear Pythonic API to try and make it the actual process of model building as simple as possible. And so it's just kind of a very quick example of, here I should probably zoom in to make this more readable. So it's just kind of a very quick example of what doing a simple typical task would be like. We're just going to run the example that's in the PyHF GitHub README. We're just going to import things. And then all we're doing here is we're just creating a very simple one bin model. So, as much of a toy example as you can get. And then we're going to, once we have this model and some simulated data, we're going to then perform a hypothesis test scan across multiple parameters of interest. We're going to plot those results and then invert them to determine a 95% confidence level upper limit on our parameter of interest value. So we can see that just in a very few lines of code, we can actually get what is known as a Brazil band plot that actually is showing kind of our observed and expected values, as well as the line that would show exclusion. And then we can, as I said, also invert those to actually get the observed limit that we have as well. So this has just been a super cursory overview, but the really important part here is that PyHF allows for statistical modeling of binned models, and it also allows for fast Pythonic fitting. But so the majority of what we're going to be talking about today is going to be focusing on how to extend this with both funcX as well as Google Cloud Platform to try and do high performance fitting as a service. So I'm first going to introduce funcX, and funcX is a high performance function as a service platform. So the goal of funcX is to provide a tool to orchestrate scientific workloads across heterogeneous computing resources. So we're talking clusters on the cloud, on supercomputers, as well as across all different task execution providers. So you can basically write one config that you can model a little or vary a little bit to be able to run on HTCondor, on Slurm, on Torch, on Kubernetes. So it is very extensible and allows you to do be able to switch where you're running with very little change to your actual setup. And it does this by leveraging Parcel, which is a flexible and scalable parallel programming library for Python that is very efficient and quite nice. Okay, so funcX endpoints are something we also need to talk about here. So they're logical entities that actually are the thing that kind of sit on a compute resource, and they are managed by an agent process that allows funcX to dispatch user-defined functions to actually run for execution. And so this is kind of the core here. You can define user functions that can then run anywhere on perhaps an HPC environment, and they can be scaled out very efficiently. Okay, so to try and give a very, very short demo of all of this, what we're going to do, since we installed funcX and the funcX endpoint, is we're going to do a kind of silly example because I didn't have things working. We're going to try and act like our local machine, in this case my laptop, is both our execution machine as well as our submission machine. So if I'm acting like I was on perhaps like my HPC center, I can just go ahead and use the funcX endpoint command line to get some information about what we have here. So the first thing we're going to do is we're going to want to configure an endpoint. And so for this, I'm actually going to open up a launcher again and open up a terminal, because it's going to be actually considerably easier to run this in the terminal than to run it in the notebook right now. So what we're going to do, here, I'll also activate this. Okay, so what we're going to do is we're going to run funcX endpoint, and then we're going to do configure actually, let me make sure I have let me make sure I have this cleaned up so I can try and make it as similar to you as possible. Okay, so if we run funcX endpoint configure PyHF, then what this is going to do is create all the configuration files necessary to set up an endpoint, and it's going to give us this Globus authorization URL. So funcX does all of its authentication and authorization through Globus. So the first time that you click on this, if you aren't already logged in, you would be taken to a Globus page for login. And if you're not familiar with Globus, it's it's a service that that does these sorts of things as well as data transfer. And if you don't have a personal account, you can either use an organizational account or your OrcID account or your Google account. So hopefully it's not too much of a barrier to entry that there's this additional layer for security in between. But since I already have this set up, I'm just going to copy this URL, drop that in there. And now simply this is just saying that, hey, you're setting up a new endpoint. Do you want to make sure that you can allow this for authorization for use of the funcX software development kit? And so we're going to allow that. We're given this authorization key. And since this is a one-time demo, it's perfectly fine that this is visible to all of you. And so we're now going to set that up. And now we get this message that we now have our endpoint configured, and we can go ahead and actually start that up. So before we do that, though, we're going to modify things just a little bit. So as we continue on in our notebook, if we actually look at what this configuration file is right now, we can see that it's basically just a few imports from both funcX and Parcel. And then we see that we basically have this configuration for the HPC provider, and it basically has these small configuration blocks on determining how the actual workflow is going to run. To make an example of this, we're also going to copy over a configuration file that I prepared beforehand and look at that again. And we're now going to see that in addition to this initialization blocks, min blocks, and max blocks, there's these additional values that I've added in that were default values, nodes per block, and parallelism. Okay, so we're going to explore just what that means a little bit, because without this, funcX might seem a little bit like just magic, and we want to try and avoid that, because you still are responsible for controlling how your compute environment works. Okay, so just to break down some terminology real quick, when we talk about blocks, we're really talking about the basic unit of computing resource that a provider like Slurm could give you. And then the max blocks is then just the maximum number of those that you can have per executor. And the nodes per block is the number of compute nodes that you can request per block. And then this value parallelism, this is basically the value that determines how scaling is going to happen versus just utilizing current resources. So if we take an example from the Parcel documentation, which funcX then extends, we can look at this where we have this minimum number of blocks is 1, this max blocks 2, nodes per block 1, and parallelism 0.5. And to try and give an example in a GIF of what that actually looks like, so on the left-hand side, we see this kind of example of having 9 tasks that we want to actually compute and execute. And so what happens is when Parcel and funcX start up, they start distributing tasks to workers available. And so we have this first compute block, and it has the ability to have 4 tasks per node on the block. And so what's happening here is those first 4 tasks are just put on there and start to execute. But then when we get to the 5th block, or the 5th task, we've actually already reached capacity for this initial block. So we now need to determine, are we going to wait for tasks on the first block to finish so that additional tasks can be added, or are we going to scale out to an additional block? And given the way, and given that we've reached a value in the task remaining that is greater than the parallelism of 0.5, what Parcel then decides to do under the hood is it decides to then allocate another block and scale out the additional resources to try and efficiently finish all the tasks. Okay, so with that kind of hopefully in mind explaining a few things, what we're going to do is then run we're going to actually start up the endpoint, and we now see that we have this process running. And if we use the funcX endpoint list function to list all the ones that we have, we now see that we have this this endpoint that's up and running with this endpoint ID. And so this is all kind of on our imaginary remote HPC center or something, but we're going to want to have access to this endpoint ID elsewhere. So we're going to then just put that into an endpoint ID text file, which you would then be able to SCP down to wherever you're running locally. And now if we kind of switch over our mindset to thinking that we're now on our local laptop or we're somewhere else, we're going to now try and set up what we're actually going to run on this endpoint that we've just set up. So here what we're doing is we're going to prepare a very, very simple example as just kind of a test function. And so here we have this simple example function that simply all it does is it basically takes a trivial model and then it makes some pseudo data from that and then just performs a single fit. And then, and you can see since we're executing functions, we need to include all of our imports inside the function definition because they're going to be sent off and run outside of a global scope of a particular file. So if we,
yeah, it's like, I don't know,
5 minutes.
60.
Okay, great.
No, it's not 5. It's just past like, I don't know, 17 minutes so of your talk. So you still have a lot of time.
Okay, great. I'll still try and speed along. So thank you very much, Oksana. Okay, so if we then look at this simple example, we see that we then get this just dictionary back, as I mentioned, that returns both the observed fit value as well as the fit time. If we were then to actually spin up the local funcX client that's going to be doing all the communication for us, we can then initialize that, and then we can register the function that we just created with the client. So the client now knows about this function, and it can now interact for us with our remote on our HPC center or something. So if we open up now this this endpoint file so that it's we have this endpoint ID known to us, then what we're going to now do is we're going to serialize this function that we just created, and we're going to have the funcX client send it over the network to this HPC center or to the endpoint wherever it is in the world, and we're going to now ask that endpoint to please execute this task for us. Of course, here, this is just happening locally, so it basically runs instantly with no time. And then in the scenario, we could like wait for a little bit, and then once we think it might be done, ideally you would do this in some sort of periodic checking loop. We can now have our local client call out to the remote center and get back and ask to get back the result, and we see that we get this back. Okay, and so in the interest of time, I'm going to kind of stop here for the funcX portion, but I'll mention that this demo wasn't super interesting because we weren't actually running on a real center, but as was shown in our VCHEP 2021 talk, when we do actually run on an HPC center using funcX and executing code locally from our laptops to then call out to it, we're able to fit 125 signal model hypotheses that are from a published Atlas analysis in a wall time of under 2 minutes and 30 seconds. And that includes includes the downloading of all the files from HEPData to a local machine, serializing them, sending them out, actually doing all the running and getting all the results back. So this can be a very powerful workflow. Okay, so in the time remaining, I'm going to now switch tasks again, and I'm going to actually kill this, and then I'm going to go to a local example of using Google Cloud Platform to try and do a similar thing. Okay, so Google Cloud is a resource that some of you might be familiar with, and I'm just going to run this in the interest of time to make sure that we get going. So Google Cloud is another way for us to try and run PyHF in a distributed manner. So what I'm doing right now is, oops, let me restart and clear all output. Sorry, hold on. Okay, this is strange. The kernel seems frozen. Let me try and restart real quick. Okay, so Google Cloud is a resource that that some of you are probably familiar with, and Google Cloud is another way for us to actually register functions with Google Cloud beforehand, and then to try and run them in a highly distributed manner. And so what we're doing right now is we're actually we're downloading a published Atlas analysis and from HEPData. So here I'm going to I'm going to copy this URL for a second and go there. So what we're doing right now is we're downloading, that's the actual tarball. We are from HEPData. We are downloading all of the files. Okay, apparently that doesn't want to work, but we're downloading all the file data for this particular analysis. And then we're sending them out in real time to Google Cloud to actually run fits. And then as those results run and come back, we're updating a plot in real time to actually see as these different fit results come in, how they update our final exclusion plot for this supersymmetry analysis. And so as this runs, you can see that as we get more CLS values back, we start to form this exclusion contour. And this is, and as we get more and more results back, this will approach the final exclusion limit. And when that's done, it will go gold. Okay, so I think since I'm over 20 minutes now, and this is just going to kind of run and update as things go on, I'm going to stop here and pivot to Slido to try and address any questions or comments that people might have. Okay, and yeah, so now, okay, that got a little bit strange, but so now we have in a runtime of just a very short number of seconds. As this, okay, it doesn't print here, but in just a few seconds, we're actually able to get this this nice plot out. So we were able to compute a couple hundred different CLS values, and I think under 2 minutes. So this is another example of how we can use distributed computing to take the Pythonic nature of PyHF and run at scale. Okay, all right, so as I said, I'm now going to switch to any questions on Slido. It seems that we have one. Is there any way for users to sync their Python environment with the funcX service? I assume imported modules need to be installed there. Yes, so that's a very good question. I would have actually shown that had I had access to the hardware today. But when you are setting up your funcX environment, your funcX endpoint, you need to recreate the runtime environment that you would need if you're going to be running locally. So that means that, let's say that you are running on some HPC center and the worker nodes would need to be able to set up a particular environment, either be it with a requirements.txt in a virtual environment, or maybe something like a Conda environment. As part of your setup in your funcX configuration file, you would have the worker call the setup script that you would normally use to activate that virtual environment. So you do need to make sure that on your endpoint, which I've just been referring to generically as an HPC endpoint, that endpoint has the ability to set up the same virtual environment that you would want if you were just running locally. Okay, I think that's the only question we have. We still have, I think, like 3 or 4 minutes. So if there's additional questions, I'm happy to answer them. And if not, then we can go ahead and get going on to other talks.
Matthew, can I ask a question? I somehow cannot type in Slido. Oh, okay, there is the other one. I will be next.
Okay. How does PyHF compare to ZFit and HEPstats? Maybe they're not correlated, but they seem to be similar. Right. So this, yeah. So thank you for being familiar with the scikit-hep ecosystem. I think maybe the thing that's the most comparable is to talk about how ZFit and PyHF differ. So PyHF focuses on bin statistical models, where ZFit is trying to do the more general thing of kind of the open world of statistical models in a similar way to what how RuFit does. PyHF focuses on binned models. PyHF, though, we are backend agnostic. So we have, oh, you mentioned, okay, sorry. Yeah, so I think this is kind of this and the question below is a good example, is probably a good example. So PyHF has, you can choose, we're backend agnostic, so you can, the default backend that we provide is NumPy with a SciPy optimizer, but we additionally support combinations of optimizers as well as computational backends for JAX, TensorFlow, and PyTorch. And so we have implementations for all of these that the user can switch out very easily. And as this kind of goes into the, okay, so I believe Jonas is going to be talking either today or tomorrow. He's going to do a full tutorial on ZFIT, and is a ZFIT backend a possibility? Possibly, however, ZFIT as of at least PyHEP 2020 is TensorFlow only, and so so this is something to explore a bit more. But I mentioned that this is pure Python, but the commenter mentions that this is often misused. C in the backend. So I guess this is well. C in the backend is a bit of an interesting comment because, I mean, you know, Python itself is in C, and I guess this kind of also gets into the question of what is a package, because I think most of us would say that SciPy and NumPy, these are Python packages, but as we know that these also have components of Fortran and C in them as well. So I guess I would say, like, when I say pure Python, I mean that that everything that the PyHF development team writes is just Python. We are not actually writing any C extensions or any Fortran extensions or anything like that. And everything that exists in PyHF is installable from PyPI or CondaForge if you want. I realize the CondaForge brings in the difficulties of the fact that you can install root with CondaForge. Great work, Chris and Henry there. But basically, I just mean it's pure Python. We only write Python in the project file, in the project itself, and everything's available on PyPI. The performance of PyHF versus the HistFactory implementation and root, I guess I would say is comparable. And in particular situations, we have been able to demonstrate that PyHF is able to outperform the HistFactory implementation and root, due to the fact that we are able to leverage this automatic differentiation as well as the highly vectorized nature of the code. That's not to say that every single instance of every single HistFactory problem that you want to run with PyHF is going to be always faster than the implementation in root, but we've noticed that in many it is.